If you are given a table of experimental data, you should always pay close attention to the data you are given. Now what I'm going to do before I give you the correct answer to question 11 is I'm going to intentionally make the common mistake that most students would make when reading this question. So what I'm about to show you is a mistake, but it's based on a very common mistake that students make. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 3.1 to 3.3. As you can see on this slide, these topics fall under Unit 3 in the AP Chemistry curriculum, Properties of Substances and Mixtures. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 3.1, Intermolecular and Interparticle Forces. Here are some essential knowledge statements from the AP Chemistry course and exam description. London dispersion forces are the result of Coulombic interactions between temporary fluctuating dipoles. London dispersion forces are often the strongest net intermolecular force between large molecules. Dispersion forces increase with increasing contact area between molecules and with increasing polarizability of the molecules. The polarizability of a molecule increases with an increasing number of electrons in the molecule and the size of the electron cloud. It is enhanced by the presence of pi bonding. The dipole moment of a polar molecule leads to additional interactions with other chemical species. Dipole-induced dipole interactions are present between a polar and nonpolar molecule. These forces are always attractive. The strength of these forces increases with the magnitude of the dipole of the polar molecule and with the polarizability of the nonpolar molecule. Dipole-dipole interactions are present between polar molecules. The interaction strength depends on the magnitude of the dipoles and their relative orientation. Interactions between polar molecules are typically greater than those between nonpolar molecules of comparable size because the interactions act in addition to the London dispersion forces. Ion dipole forces of attraction are present between ions and polar molecules. These tend to be stronger than dipole-dipole forces. The relative strength and orientation dependence of dipole-dipole and ion-dipole forces can be understood qualitatively by considering the sign of the partial charges responsible for the molecular dipole moment and how these partial charges interact with an ion or with an adjacent dipole. Hydrogen bonding is a strong type of intermolecular interaction that exists when hydrogen atoms, covalently bonded to the highly electronegative atoms, nitrogen, oxygen, and fluorine, are attracted to the negative end of a dipole formed by the electronegative atom, nitrogen, oxygen, and fluorine, in a different molecule, or a different part of the same molecule. In large biomolecules, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. Now let's move on to the practice for topic 3.1. This is question 1. In question 1, it says an equimolar mixture of chlorine gas and bromine gas is cooled until each substance condenses. Which of the following indicates the gas that condenses at the lower temperature and gives a particle level explanation for why? Now, before we consider the four choices in question 1, let me present a scenario with substances A and B. So suppose you have two different substances that are liquids at room temperature, and they are labeled as A and B, and pure samples of each substance are placed into separate beakers, and the beakers are heated gently. Now, at a temperature of 310 kelvins, substance A reaches its boiling point. Substance B has not reached its boiling point yet. So substance A has the lower boiling point. Substance B has the higher boiling point. So let's assume that substance B has a boiling point of 350 kelvins. Now, if we turn each of these substances completely into a gas, then we consider what's happening in question 1. So let's get them both into the gas phase. So I have a container with 400 kelvins as the temperature. There's a mixture of substances A and B, and because we're at 400 kelvins, both substances are in the gas phase, because the temperature inside the container is greater than the boiling point of both substances. Now think about what will happen inside this container when the temperature is decreased. In question 1, it's asking us to predict the substance that will condense at the lower temperature. So the substance that condenses at the lower temperature is the one that has the lower boiling point and has weaker attractive forces between its particles. So if we cool this gas mixture, then at around 350 Kelvin, substance B will start to condense. That's the one that has the higher boiling point and stronger attractive forces between its particles. But what about that lower temperature? So at around 310 kelvins, which is a lower temperature, now substance A will start to condense, and that is the substance that has the lower boiling point and has weaker attractive forces between its particles. So the substance that condenses at the lower temperature is the one that has the lower boiling point and has weaker attractive forces between its particles. Now that we know that, let's go back and consider the choices in question 1. We are comparing chlorine and bromine. And when you look at the Lewis diagrams for these two molecules, it seems like they are the same, but remember that a Lewis diagram is only showing you the valence electrons. So while chlorine and bromine both have a total of 14 electrons in these two very similar Lewis diagrams, in fact, when we consider the information on the periodic table as far as atomic number, chlorine, the molecule Cl2, has 17 times 2, or 34 total electrons in that molecule. On the other hand, bromine, that would be Br2, has 35 times 2, or 70 total electrons in that bromine molecule. And we are looking for the weaker attractive forces. So in this case, these two nonpolar molecules only experience London dispersion forces between them. And since chlorine, Cl2, has fewer electrons than bromine, then the Cl2 molecule is a smaller, less polarizable electron cloud, and there would be weaker attractions, weaker London dispersion forces between molecules of chlorine. So we know that chlorine is the correct answer to question 1, so I can eliminate choices C and D. It's not because chlorine atoms are more electronegative than bromine. We are comparing the relative strength of the London dispersion forces between the molecules. So the correct answer to question 1 is choice B. So chlorine will be the gas that condenses at the lower temperature because the dispersion forces in liquid chlorine are weaker than the dispersion forces in liquid bromine. All right, now let's take a look at question 2. Now, what makes question 2 a little different than question 1 is that we're not making a prediction in question 2. We're given a data table. So back in question 1, we had to determine which substance was going to have weaker or stronger intermolecular attractive forces. But here, we are given the chemical name, the chemical formula, the structural formula, the molar mass, and the boiling point. So the question is asking which of the following statements best helps explain why cyclopentanone has the higher boiling point. So we can see that 403 kelvins is greater than 354 kelvins. So what we're looking for in question 2 is an explanation at the particle level for why there are stronger attractions between molecules of cyclopentanone, which is C5H8O, and why there would be weaker attractive forces between molecules of cyclohexane, which has the chemical formula C6H12. So we have cyclopentanone, C5H8O. It has a molar mass of 84.1, and it has the higher boiling point. And then we have cyclohexane, C6H12, a very similar molar mass, and it has the lower boiling point. Now you may remember from topic 2.7, which involves VSEPR and molecular geometry, that when you look at the shape of a molecule, you should be able to determine if that molecule will be polar or not. So the fact that there is a carbon-oxygen bond in cyclopentanone, that particular polar bond is not going to be canceled out by anything else in that molecule. So that is definitely a polar molecule in which the bond dipoles do not cancel out. And then based on the symmetry of the molecule cyclohexane, that is nonpolar. And you may also know that a carbon-hydrogen bond is generally considered to be a nonpolar bond in terms of the AP chemistry curriculum. So most molecules that contain only carbon and hydrogen will fall into the category of being nonpolar. So we have a polar molecule on the left, we have a nonpolar molecule on the right, and you should know that nonpolar substances can only experience London dispersion forces between the molecules. But if you are a polar molecule, then in addition to London dispersion forces, you also can experience what we know as dipole-dipole attractive forces between the molecules. So the fact that cyclopentanone experiences a combination of both London dispersion forces and dipole-dipole attractive forces, then that's going to be the explanation for why there are stronger attractive forces between molecules of cyclopentanone, which will lead to a higher boiling point. Now, the first choice in question 2 is a very common misconception for students, but that is an incorrect choice. We are not breaking covalent bonds within the molecule. So whenever a substance changes from a liquid to a gas or a solid to a liquid, and it's only composed of molecules, we are only breaking the attractive forces between the molecules during phase changes. We are not breaking the actual covalent bonds. So we can eliminate choice A. It's not about comparing a carbon-oxygen double bond to a carbon-carbon single bond. Now in choice B, they do talk about the dipole moment, but they're referring to a substance that is nonpolar. It says the dipole moment of the cyclohexane molecule is larger than that of the cyclopentanone. And since cyclohexane is nonpolar, it has a dipole moment of 0, so it would not be considered polar at all. So we can eliminate choice B. And then in choice C, it says that each substance only experiences London dispersion forces. But we know that since cyclopentanone is polar, it will also experience dipole-dipole interactions. So we can eliminate choice C. The correct answer for why cyclopentanone has the higher boiling point is because cyclohexane, which is nonpolar, only experiences London dispersion forces. But cyclopentanone, which is polar, experiences a combination of London dispersion forces and dipole-dipole interactions. So the correct answer to question 2 is choice D. Now let's take a look at question 3. In question 3, it says 2 cations are shown above. That's Na plus and K plus. And it says which of the following correctly identifies the cation that experiences the stronger attraction to a water molecule in solution and provides the correct justification. So we're talking about what are known as ion dipole attractive forces. We're going to use Coulomb's law to make this comparison to decide whether it's Na plus or K plus that has the stronger attraction to a water molecule in solution. Now, the numerator of Coulomb's law involves the magnitude of the charges on the particles. So if there were a different magnitude of charges on these ions, then the ion that has the greater charge magnitude would have the stronger attraction toward that polar water molecule. But since both Na plus and K plus have the same charge magnitude, it won't be about the charge magnitude, it's going to be about the distance, and that's the R squared in Coulomb's law. So if the ion has a smaller ionic radius, then there is a smaller distance between the ion and the polar water molecule, resulting in a stronger attractive force, a stronger ion-dipole attractive force. So which of these ions has the smaller ionic radius? Now, sodium has 11 electrons on the periodic table, but then sodium plus has lost an electron. So it has 10 electrons, 1s2, 2s2, 2p6. It has 2 occupied electron shells. Potassium, the atom, has 19 electrons, and then K plus, the ion, has 18 electrons, but that would go all the way to 3s2, 3p6. K plus has a greater number of occupied electron shells. Na plus has a smaller number of occupied electron shells. Now that makes Na plus the one with the smaller ionic radius, and that's the answer that we're looking for. So the correct answer to question 3 is choice C. We're choosing Na plus because it has a smaller radius, and that results in a smaller distance between the ion and the water molecule and a stronger attractive force between them. So the correct answer to question 3 is choice C. Now let's take a look at question 4. In question 4, it says the structures and boiling points for C3H7OH and C3H7SH are shown below. And in part A of this question, it says, in the table above, list all of the types of intermolecular attractive forces present in pure samples of each of these substances. Now, we can start off with London dispersion forces because all molecules, whether they are polar or nonpolar, would experience that type of attractive force between the molecules. Let's consider if each of these molecules would be polar or nonpolar. Hopefully you can see that C3H7OH does not have that perfect symmetry in which the bond dipoles would cancel each other out. So C3H7SH, same thing, there's not perfect symmetry among the bonds in that molecule. So each of these molecules would be classified as polar because the bond dipoles are not going to cancel each other out. So we can say with confidence that both C3H7OH and C3H7SH would experience both London dispersion forces between the molecules as well as dipole-dipole attractive forces between the molecules. So the next thing for us to consider in part A of question 4 is hydrogen bonding attractive forces. So in my video for topic 3.1, I had presented the information on this slide. Hydrogen bonding is an important type of attractive force that involves the following details. One substance behaves as a hydrogen bond donor, and the other substance behaves as a hydrogen bond acceptor. So here are the requirements for a substance to be a hydrogen bond donor. The substance needs to contain a hydrogen atom that is covalently bonded to a highly electronegative atom, specifically nitrogen, oxygen, or fluorine. And then the other substance to behave as a hydrogen bond acceptor contains this highly electronegative atom, specifically nitrogen, oxygen, or fluorine, and it's going to have a lone pair of electrons on it. It's going to have a partial negative charge on it because it's part of a polar bond, a bond dipole. So here are a few examples. These are two molecules of NH3. There's the hydrogen bonding attraction between these molecules, and one molecule serves as the hydrogen bond donor. The other molecule serves as the hydrogen bond acceptor. Here are two molecules of water. Here's the hydrogen bonding attractive force between them. One molecule serves as the hydrogen bond donor. The other molecule serves as the hydrogen bond acceptor. Here's a similar situation with two molecules of HF, where you have a hydrogen bond donor and a hydrogen bond acceptor. Now, back to question 4 in this packet. I'll highlight that C3H7OH does contain a hydrogen atom directly bonded to oxygen, so that substance would also experience hydrogen bonding attractions between its molecules, but not for C3H7SH. So now we have answered part A of question 4. And this is very helpful that we know that one substance would experience hydrogen bonding attractions, whereas the other substance would not, because there is a difference in their boiling points. So in part B of question 4, it says, based on the types and relative strengths of the intermolecular forces in each substance, explain why the boiling point of C3H7OH is higher than that of C3H7SH. So in answering part B of question 4, you should do at least 2 things. You've already listed the types of intermolecular attractive forces, but I'm highlighting that hydrogen bonding is present in one substance, but not in the other substance. So hydrogen bonding should be part of your explanation and answer in part B, and you should also use the word stronger or weaker in your answer. So this is what I said in my answer to part B of question 4 in this packet. I said the presence of hydrogen bonding in liquid C3H7OH results in the total intermolecular attractions in that substance being stronger than the total intermolecular attractions in the other substance. And I'll just mention that the details of what I had said in part B of this question will be something I will bring up at the end of this lesson, where I give you advice to avoid common mistakes. Okay, now let's move on to the review for topic 3.2, properties of solids. Here are some essential knowledge statements from the AP Chemistry course and exam description. Many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. Because intermolecular interactions are overcome completely when a substance vaporizes, changing from a liquid to a gas, the vapor pressure and boiling point are directly related to the strength of those interactions. Melting points also tend to correlate with interaction strength, but because the interactions are only rearranged in melting, the relations can be more subtle. Particulate level representations showing multiple interacting chemical species are a useful means to communicate or understand how intermolecular interactions help to establish macroscopic properties. Due to strong interactions between ions, ionic solids tend to have low vapor pressures, high melting points, and high boiling points. They tend to be brittle due to the repulsion of like charges caused when one layer slides across another layer. They conduct electricity only when the ions are mobile, as in when the ionic solid is melted, that is, in a molten state, or dissolved in water or another solvent. In covalent network solids, the atoms are covalently bonded together into a three-dimensional network, for example, diamond, or layers of two-dimensional networks, for example, graphite. And these are only formed from nonmetals and metalloids, elemental, for example, diamond and graphite, which is carbon, or binary compounds, for example, silicon dioxide and silicon carbide. Now, due to the strong covalent interactions, covalent solids have high melting points. Three-dimensional network solids are also rigid and hard because the covalent bond angles are fixed. However, graphite happens to be soft because adjacent layers can slide past each other relatively easily. Molecular solids are composed of distinct individual units of covalently bonded molecules attracted to each other through relatively weak intermolecular forces, which was mentioned in topic 3.1. Molecular solids generally have low melting points because of the relatively weak intermolecular forces present between the molecules. They do not conduct electricity because their valence electrons are tightly held within the covalent bonds and the lone pairs of each constituent molecule. Molecular solids are sometimes composed of very large molecules or polymers. Metallic solids are good conductors of electricity and heat due to the presence of free valence electrons. They also tend to be malleable and ductile due to the ease with which the metal cores can rearrange their structure. In an interstitial alloy, interstitial atoms tend to make the lattice more rigid, decreasing malleability and ductility. Alloys typically retain a sea of mobile electrons and so remain conducting. In large biomolecules or polymers, non-covalent interactions may occur between different molecules or between different regions of the same large biomolecule. The functionality and properties of such molecules depend strongly on the shape of the molecule, which is largely dictated by non-covalent interactions. Now let's move on to the practice for topic 3.2. This is question 5. In question 5, it says the Lewis diagrams for compounds X and Y are given above. Which of the following identifies the substance that has the higher boiling point and provides a valid justification? The first thing I'm going to do is eliminate 2 of the 4 answer choices listed in question 5 because they are based on a common misconception that you should be aware of, and that is when we are changing these molecular substances from a solid to a liquid or a liquid to a gas, we are not breaking the covalent bonds within these molecules. Instead, we are breaking some of the attractive forces between the molecules, and breaking the attractive forces between the molecules would be either London dispersion forces, or dipole-dipole interactions, or hydrogen bonding attractions. Now I can see that in choice B, it says triple bonds are harder to break than single bonds. But again, we are not breaking covalent bonds within these molecules when we're changing them from a liquid to a gas. Similarly, I'm going to eliminate choice D. It's not about comparing the carbon-chlorine bonds and the carbon-hydrogen bonds. Those are covalent bonds within the molecule, and we're not breaking them when we change these substances from a liquid to a gas. So it comes down to the London dispersion forces. Now you may already have recognized that these molecules are very symmetrical. They would both be classified as nonpolar because the bond dipoles in each of these molecules are either going to cancel each other out, as in compound Y, where those polar carbon-chlorine bonds are all arranged symmetrically in such a way that they would cancel each other out, or the fact that compound X contains only carbon and hydrogen. It's also very symmetrical as well. But typically a molecule that contains only carbon and hydrogen tends to be nonpolar. So what it comes down to is which of these molecules has a larger electron cloud. Now hydrogen only has 1 electron, but chlorine has 17 electrons, and there are 6 chlorine atoms in the molecule for compound Y. So hopefully you can see that compound Y has a much larger electron cloud than compound X. Again, nonpolar molecules only experience London dispersion forces. Compound Y has more electrons than compound X. So compound Y has a larger, more polarizable electron cloud, which leads to stronger London dispersion forces between the molecules. So the correct answer to question 5 is choice C. Compound Y should have the higher boiling point because the London dispersion forces among molecules of compound Y would be greater than those among compound X. Now let's take a look at question 6. Now in question 6, we have a data table and the boiling points are given, but only one of the values for the equilibrium vapor pressure is given. There's a question mark next to CH3, CH2, CH2OH liquid. And so the question asks, based on the information in the table above, which of the following correctly describes the equilibrium vapor pressure of this liquid at 298 Kelvin and provides a valid justification? Now in this lesson, we have not yet talked about equilibrium vapor pressure. So let me go ahead and teach you important concepts to be aware of when you are comparing things such as the strength of the attractive forces, the boiling point, and the vapor pressure. So on this slide, this was a graphic that I had presented in my video for topic 3.2. And you can see that on this graph, there's vapor pressure on the y-axis, and there's the temperature on the x-axis. Now, water comes to a boil at standard atmospheric pressure at a temperature of 100 degrees Celsius. That's the normal boiling point of water. The other substance, which is ethanol in this diagram, it comes to a boil at approximately 78 degrees Celsius. And the takeaway from this diagram is higher vapor pressure for ethanol, lower boiling point. On the other hand, lower vapor pressure for water, higher boiling point. Now I'll compare these two liquids with a different graphic. This also came from my video for topic 3.2. So on the left, we can see that water at 20 degrees Celsius has a vapor pressure of 17.5 torr. Ethanol at that same temperature of 20 degrees Celsius has a higher vapor pressure of 44.6 torr. So what we're seeing on the left would be higher boiling point for water, lower boiling point on the right for ethanol, higher boiling point, stronger attractions between molecules, lower vapor pressure for water. On the other hand, lower boiling point, weaker attractions between the molecules, higher vapor pressure for ethanol. So now that's the end of that little mini lesson on boiling point and vapor pressure. You should know that they are inversely related. So a higher boiling point would correspond to a lower vapor pressure. Now back to the diagram and the table for question 6. So because that substance that has a higher boiling point of 371 Kelvin should have a lower vapor pressure, the correct answer to question 6 would be less than 127 torr. Let's take a look at our 4 answer choices. So since less or lower than 127 torr is the correct answer to question 6, I will go ahead and eliminate choices C and D. Now, with respect to the hydrogen bonding, there is a hydrogen directly bonded to an oxygen in each of these molecules. Each of these molecules has only one site on the molecule where it can behave as a hydrogen bond donor. So let's take a look at the justification in choice B. It says the number of hydrogen bonds among the CH3, CH2, CH2OH molecules is greater than those among CH3OH molecules, but there's no difference in the number of hydrogen bonds between the molecules. Each molecule has one site where the molecule can behave as a hydrogen bond donor. So I can eliminate choice B. So the correct answer to question 6, which of the following correctly describes the equilibrium vapor pressure of that CH3, CH2, CH2OH liquid? It is going to be lower than 127 torr, and the reason why has to do with the London dispersion forces. Let me go ahead and put these molecules side by side. You can see that one of them does have a larger electron cloud. So that particular molecule, the CH3, CH2, CH2OH, has a larger, more polarizable electron cloud and therefore stronger London dispersion forces between its molecules. So correct answer to question 6 is choice A. Now let's take a look at question 7. Question 7 says, which of the following could be the identity of a crystalline solid that exhibits the following properties? It melts at 338 degrees Celsius, it does not conduct electricity as a solid. It conducts electricity in an aqueous solution. So I'm going to classify each of the four choices in question 7 into one of the four following categories, and this is from the content for topic 3.2, including the types of solids. So what are the four types of solids that you should be familiar with in AP Chemistry? They are ionic, covalent network, molecular, and metallic. And you will see more information about the types of solid if you watch my YouTube video that includes topic 3.2. Now, one of the choices in question 7 was the element tin, and tin has the elemental symbol Sn. And as you can see, tin is classified as a metal. So in choice D, tin is a metallic solid. It is a substance that can conduct electricity as a solid because of the mobile valence electrons. So our particle level view of a metallic solid is that there is a sea of delocalized valence electrons, and that's why metals are good conductors of electricity. It can also explain why metals are malleable and ductile. All right, so choice D is tin, which is a metallic solid. Now in choice C, we can see a chemical formula with capital B, capital N, that represents the elements boron and nitrogen. So the compound listed in choice C is boron nitride. Boron nitride happens to be an example of a covalent network solid, where there's an extended network of covalent bonds between the atoms. These substances tend to have very high melting points, and they're very hard and rigid, and that's because of that extended network of strong covalent bonds in all directions. So most covalent network solids, their melting points could be well over 1,000 degrees or more, 1,000 degrees Celsius. So in choice C, boron nitride, that is a covalent network solid. Now in choice B, we have a compound that has a chemical formula C2Cl6. Since carbon and chlorine are both classified as nonmetals, it is likely that when two nonmetals are bonded together, you're going to form a molecular solid. So molecular solids consist of molecules. You can see examples that involve nonmetals such as carbon, hydrogen, oxygen, nitrogen, fluorine, chlorine, etc. And they consist of molecules, individual molecules, and they're held together by the intermolecular attractions between the molecules. They tend to be relatively low melting points. And then the last type of solid is ionic. So by the way, in question 5, C2Cl6 was actually used. So if you think when you're looking at question 7, haven't we seen that chemical formula before? That molecule did appear back in question 5. All right, so ionic solids tend to be metals and nonmetals bonded together. So in the examples listed at the bottom of this slide, I have lithium bromide, sodium nitrate, magnesium oxide, potassium chloride. So in general, you would expect a typical binary ionic compound to consist of a metal and a nonmetal. So you might be wondering, is there an ionic solid listed here in question 7? Well, we have in chemistry what are called monoatomic ions consisting of only one atom, but then we also have polyatomic ions such as phosphate, carbonate, sulfate, chromate, hydroxide, nitrate, and you can see ammonium is a polyatomic ion. Ammonium is NH4 plus 1. So in choice A, that is classified as an ionic compound even though there is no metal in that formula. So it contains ammonium ions and chloride ions. Now, what does an ionic solid do in terms of its properties? It tends to be the following. It does not conduct electricity as a solid, but it does conduct electricity in either aqueous solution or when melted. So it does not conduct electricity as a solid because the charged particles, the ions, are unable to move freely in that rigid crystal lattice. But when either melted or dissolved in water, an ionic substance can conduct electricity. So from the description in number 7, we were looking for an ionic substance. So the correct answer to question 7 is choice A. Solid ammonium chloride is an ionic substance. Choice B, C, and D are examples of a molecular, a covalent network, and a metallic solid. Okay, now let's take a look at question 8. In question 8, we are given a data table with 2 different substances. We can see the Lewis diagram and the boiling point, and it says complete Lewis diagrams and some physical properties for chlorine, Cl2, and C2H5Cl are given above. Now, we can see from the data in the table that C2H5Cl does have the higher boiling point. So a student claims that C2H5Cl has a higher boiling point than that of chlorine because the hydrogen bonding attractions between C2H5Cl molecules are stronger than the London dispersion forces between chlorine molecules. Do you agree or disagree with the student's claim? Justify your answer. Let's consider these 2 molecules and look at the Lewis diagrams. Are each of these molecules polar? Are each of these molecules nonpolar? Or is there one of each? Hopefully you can tell that when you have 2 of the same identical element or atom bonded together, then that would be a nonpolar Cl2 molecule. Now we do have some polar bonds in C2H5Cl, and we don't have perfect symmetry, so those polar bonds or the bond dipoles in C2H5Cl are not arranged in so that they would not cancel each other out. So based on that lack of perfect symmetry, C2H5Cl is classified as a polar molecule. So what we can say for sure is that C2H5Cl would experience a combination of London dispersion forces and dipole-dipole interactions. So what about the hydrogen bonding? Remember that in order for a substance to behave as a hydrogen bond donor, then the hydrogen must be directly bonded in that molecule to either nitrogen, oxygen, or fluorine. And we don't see nitrogen, oxygen, or fluorine in C2H5Cl. So we have London dispersion forces, because all molecules will experience that intermolecular attractive force. We have dipole-dipole forces within molecules of C2H5Cl, because that molecule is classified as a polar molecule. The bond dipoles do not cancel out. But that's it. So student makes the claim that there are hydrogen bonding attractions between C2H5Cl molecules. Let's disagree with the student's claim. So what I said was, since the hydrogen atoms in C2H5Cl are directly bonded to carbon, not nitrogen, not oxygen, not fluorine, then there are no hydrogen bonding attractions between C2H5Cl molecules. Instead, the reason for that higher boiling point is the combination of London dispersion forces and dipole-dipole forces in a sample of liquid C2H5Cl would be stronger than the London dispersion forces between molecules of Cl2. Hopefully that makes sense. That's the answer to question 8. Now let's take a look at question 9. In question 9, we are given 2 chemical formulas, SiH4, which has the lower boiling point of 161 kelvins, and then SiO2, which has a much higher boiling point of 3,220 kelvins. And number 9 says, use principles of interparticle forces to explain the difference in the boiling points shown in the table above. Now, on the periodic table, we have nonmetals, such as oxygen or chlorine, but then silicon is actually a metalloid. And so you might say, I'm not sure if that's going to be molecular or covalent network. Let me go ahead and remind you of something that I had presented earlier in this lesson. And you may remember I talked about boron nitride as an example of a covalent network solid. Other examples of covalent network solids include diamond, graphite, which are examples of carbon, silicon, and then something called silicon carbide, or SiC, and quartz. Quartz is a chemical formula, SiO2, an example of a covalent network solid. That needs to be featured in your answer to question 9. And I'll just mention to you that question 9 was adapted from the 2021 AP Chemistry exam. So in 2021, this particular free response question looks like this. It says 2 compounds that contain silicon are SiO2 and SiH4. And they had mentioned that at 161 kelvins, SiH4 reaches the boiling point, but SiO2 remains a solid using principles of interparticle forces. Explain the difference in the boiling points. You'll notice that it says interparticle and not intermolecular. That's because this is a covalent network solid, SiO2, and it's not one individual molecule, but a huge network of covalent bonds. Okay, now here is the official answer to this question from the scoring guidelines for the 2021 AP Chemistry free response section. It said that SiH4 is composed of molecules for which the only intermolecular forces are London dispersion forces. On the other hand, SiO2 is a network covalent compound with covalent bonds between silicon and oxygen atoms. Again, extended network of covalent bonds. So the London dispersion forces between molecules of SiH4 are much weaker than the strong covalent bonds between all of the atoms of silicon and oxygen in that network covalent compound. So that's why the SiH4, with its weaker attractions, has a much lower boiling point. So again, there's my official answer to question 9. And now let's take a look at question 10. Question 10 says that solid MgO, which is magnesium oxide, is not able to conduct electricity, but liquid magnesium oxide is a good conductor of electricity. A student draws the particulate diagram shown above on the right to represent a sample of liquid magnesium oxide. So part A of question 10 says identify the error in the student's drawing. Now you may already know that magnesium is a metal and oxygen is a nonmetal, and from the look of that diagram we're looking at an ionic substance. Back in question 7 we talked about ammonium chloride as an example of an ionic solid that conducts electricity only when dissolved in water, but also melted would be another example of how you can get the ions to move and flow. Now I just said the word ions. That's going to be the problem with the student's drawing. So if you look at solid magnesium oxide, those gray and white circles would represent the negative and positive ions. So the smaller white circles would be the magnesium ions. The larger gray circles represent the oxide ions. And when this is dissolved in water, it would break up into separate ions surrounded by water molecules. But even when it's melted, then those ions would separate from each other and begin to move and flow. And that's why liquid magnesium oxide is a good conductor of electricity. Now, I just talked about ions. The problem with the student's drawing is that looks more like a molecule. That does not look like separate positive and negative ions. So the problem with the student's particulate diagram is that the gray and the white circles are touching each other, and it makes it look like a molecule instead of separate ions. So this is what I said as far as the description of the error in the student's drawing. The particles shown in the student's drawing appear to be diatomic molecules, 2 circles touching each other. Now, when a binary ionic solid like magnesium oxide or sodium chloride or potassium bromide is melted, the positive ions and the negative ions are mobile and can move and flow. So how should the particulate diagram look instead of what the student drew? The particulate diagram should show individual circles to represent the ions with some empty spaces between them to show that they can now move and flow and they're not locked in that rigid crystal solid where they're much, much closer together. So part B, In the box below, draw a particulate diagram that is a better representation of a sample of liquid magnesium oxide. So here's just one example. You can see that the gray and the white circles are not touching each other to form molecules, but they are simply farther apart from each other than in the solid crystal lattice. So that particle diagram is to represent the mobile ions, which is why a sample of liquid magnesium oxide does conduct electricity. Now let's move on to the review for topic 3.3, solids, liquids, and gases. Here are some essential knowledge statements from the AP Chemistry course and exam description. Solids can be crystalline, where the particles are arranged in a regular three-dimensional structure, or they can be amorphous, where the particles do not have a regular orderly arrangement. In both cases, the motion of the individual particles is limited, and the particles do not undergo overall translation with respect to each other. The structure of the solid is influenced by interparticle interactions and the ability of the particles to pack together. The constituent particles in liquids are in close contact with each other, and they are continually moving and colliding. The arrangement and movement of particles are influenced by the nature and strength of the forces, for example, polarity, hydrogen bonding, and temperature between the particles. The solid and liquid phases for a particular substance typically have similar molar volume, because in both phases the constituent particles are in close contact at all times. Now, in the gas phase, the particles are in constant motion. Their frequencies of collision and the average spacing between them are dependent on temperature, pressure, and volume. But because of this constant motion and minimal effects of forces between particles, a gas has neither a definite volume nor a definite shape. Now let's move on to the brief practice for topic 3.3. There's only one more question left in this packet. This is question 11. Question 11 says the following. Some physical properties of bromine, Br2, and hydrogen bromide, HBr, are listed in the table above. A chemist adds equimolar amounts of gaseous bromine and gaseous hydrogen bromide to a previously evacuated rigid 10-liter container at a temperature of 350 Kelvin. Now, if you look at the data in the table, notice that the boiling points are either 206 kelvins or 332 kelvins. The fact that the temperature in the container is 350 kelvins would mean that both of these substances have already boiled. So the chemist starts off with two substances that are both gases, because the temperature is greater than the boiling point of either substance. Now, the temperature of the gas mixture is now cooled to 295 kelvins. One of the substances in the mixture condenses, while the other substance remains in the gaseous state. Using the legend given, draw 3 molecules of each substance in the sealed container represented below at a temperature of 295 Kelvin when one of the substances has condensed, but the other substance remains in the gaseous state. So for topic 3.3, solids, liquids, and gases, this particular question would like to see if you can put the particles close together, if they're in the liquid state, and then put those particles far apart from each other if they're in the gaseous state. Now, here is your warning before I draw the particles in this diagram. Be careful. If you are given a table of experimental data, you should always pay close attention to the data you are given. Now what I'm going to do before I give you the correct answer to question 11 is I'm going to intentionally make the mistake, the common mistake that most students would make when reading this question. So what I'm about to show you is a mistake, but it's based on a very common mistake that students make. So what have I done right now? I'm writing that HBr is polar, and I'm writing that Br2 is nonpolar. That is correct. HBr is polar, and Br2 is nonpolar. But here comes my mistake. I'm assuming that the polar substance would have stronger attractive forces than the nonpolar substance. So what I've done is I'm assuming that the nonpolar bromine, Br2, would exist as a gas with weaker attractive forces, and that the polar HBr, with its stronger attractive forces, in my opinion, is going to be a liquid. What I just did was ignore the data in the table. I assumed that the polar substance would always have stronger attractive forces than the nonpolar substance, but it turns out that Br2 has 35 times 2 or 70 electrons, whereas HBr has 1 plus 35 or 36 electrons. So what are we comparing in question 11? A nonpolar substance that has a much larger electron cloud and a polar substance that has a much smaller electron cloud. Now, this is not the correct answer, but I made a mistake, and that was to ignore the data in the table. Now, what does the data in the table tell us about the boiling points? Well, we are at 295 kelvins. So at 295 kelvins, bromine has not reached its boiling point yet. Bromine boils at 332 kelvins. That means that at 295 kelvins, bromine is actually a liquid. And what about the boiling point of HBr? Well, HBr has already boiled at 206 Kelvin, which means at 295 Kelvin, HBr exists as a gas. So again, pay attention to the data, because at 295 Kelvin, bromine is a liquid. And that's why I'm showing you the correct drawing for question 11. I put 3 molecules of Br2 at the bottom of the container close together to indicate that Br2, bromine, is actually a liquid at 295 Kelvin. And then I put 3 molecules of HBr near the top of the diagram with lots of empty space between them to indicate that HBr at 295 Kelvin exists as a gas. So again, be careful. If you're given a data table with experimental data, you should always pay close attention to the data that you are given. Now, some of you might be thinking, is it possible that a nonpolar molecule would have stronger intermolecular attractions than a polar molecule? And the answer is yes. It is possible that a nonpolar molecule, such as Br2, with a large electron cloud, can have stronger intermolecular attractive forces than a smaller polar molecule, such as HBr. And now if you're thinking, well, how would I have known that? The answer is you didn't have to predict that. All you had to do to answer question 11 was look carefully, paying attention to the data that you were given, which says that Br2 boils at a higher temperature than HBr. All right, well, hopefully that answer to question 11 makes sense. And now we have come to the part of the lesson where I give you advice to help you avoid common mistakes. So the first thing that I'd like to mention is that some of you watching this episode of AP Chemistry Review and Practice might feel like you need more examples of questions involving intermolecular or interparticle attractive forces, or more examples with solids and liquids and the types of solids and ion dipole forces. So feel free to check out my videos for topics 3.1 and 3.2, and the links to those videos are in the video description area below this video. I will then say what I usually say at this point in the lesson: read the question carefully and make sure you are answering the question that is being asked. My next piece of advice has to do with reviewing previous topics. So your knowledge of the content and the concepts from previous units may be needed when determining the types of intermolecular attractive forces present among molecules. For example, how do I know if a bond is polar or nonpolar? You might need to review topic 1.7, periodic trends, especially areas such as electronegativity or atomic radius, topic 2.1, types of chemical bonds, and topic 2.7, which includes VSEPR. The shapes of molecules are very important concepts in determining if a molecule is polar, where the bond dipoles do not cancel each other out, or nonpolar, where the bond dipoles do cancel each other out. So reviewing those topics may be helpful. It's very important that you know the difference between intramolecular, that means within a molecule, and these are attractive forces also known as covalent bonds, whereas intermolecular, those are attractive forces between the molecules. And so when a molecular substance, such as H2O or CO2, undergoes a phase change, such as melting or evaporation, covalent bonds are not broken during that process or that phase change. Now, in your responses on the AP Chemistry exam, avoid phrases that may cause confusion about your meaning. So here's one example. You write that ammonia, or NH3, has hydrogen bonds. And that's confusing because it might be interpreted as the actual bonds within the molecule. So instead, say that there are hydrogen bonding attractions between NH3 molecules. Another example is a student says that water has a higher boiling point because it takes more energy to break up the water molecules. Now, to break up the water molecules, do you mean break the actual molecules apart into atoms? Are we talking about covalent bonds? So instead, say it takes more energy to break the attractive forces between the water molecules. So just be very clear with your language. Otherwise, it might sound like you're talking about the actual covalent bonds instead of the intermolecular attractive forces between the molecules. Now, comparing the electronegativity values of two different elements can be helpful when you are evaluating a polar covalent bond. But there is a difference between a polar molecule and a polar bond. Molecules, especially when there's more than two atoms, can be linear, bent. You could have trigonal planar, trigonal pyramidal, tetrahedral. So you should not be discussing electronegativity when you're comparing the strength of the attractive forces between molecules. Electronegativity is more a topic for a single polar covalent bond. All right, my next piece of advice is what I had mentioned in question 11. Pay attention to the given experimental data, and this is especially true when the data seems to contradict the predictions that you might have made on your own based on the molecular structure, polarity, and the types of intermolecular attractive forces present in each substance. And yes, it is possible that a nonpolar molecule with a large electron cloud can have a higher boiling point than a polar molecule with a small electron cloud. Here's another example. Octane, which has the chemical formula C8H18, is a nonpolar molecule. And it also has a very large polarizable electron cloud. On the other hand, water, H2O, is a polar molecule with a rather small electron cloud. So you might be surprised to discover that octane has a boiling point of 125 degrees Celsius, whereas water has a boiling point of 100 degrees Celsius. So it turns out that there are stronger intermolecular attractive forces present between octane molecules than there are between water molecules. Now, suppose that you compare two different nonpolar molecules, such as chlorine, Cl2, and bromine, Br2. And suppose that one molecule, that would be bromine in this example, has a larger, more polarizable electron cloud. The molecule with the larger electron cloud should experience stronger London dispersion forces and have a higher boiling point. And so we've seen that with chlorine and bromine. Now suppose you compare two different molecules whose electron clouds are approximately the same. You may recall in this lesson we had cyclopentanone, that was C5H8O, and then we compared that with cyclohexane, C6H12. They had approximately the same size electron clouds. One molecule was nonpolar, that was cyclohexane, and the other molecule was polar, that was cyclopentanone. Now the polar molecule should experience stronger intermolecular attractive forces, and that is because of the combination of London dispersion forces and dipole-dipole forces, whereas the nonpolar substance would only experience London dispersion forces. So we would predict that the polar substance in that example should have a higher boiling point. But now we come to the last bullet on this particular slide. This is the one that ends with the phrase, pay attention. So suppose that you compare two different substances. One substance is a nonpolar molecule with a larger electron cloud, such as bromine, Br2. The other substance is a polar molecule with a smaller electron cloud, such as HBr. Now, in this situation, you cannot make a prediction about which substance will have stronger intermolecular attractive forces. Therefore, pay attention to the given experimental data. All right, a few more pieces of advice to give you here. Comparing the molar masses of two different substances is not the correct way to explain why one substance experiences stronger London dispersion forces. If you use the mass as your argument, one of them is heavier or has a greater molar mass, you will not earn the point for your response on the AP Chemistry exam. Instead, you should state that one substance has a larger, more polarizable electron cloud, which results in stronger London dispersion forces between the molecules. This next piece of advice has to do with particle diagrams. Be familiar with the structural features necessary for a molecule to behave as a hydrogen bond donor or to behave as a hydrogen bond acceptor. Practice drawing dashed lines to show the correct hydrogen bonding interactions between two molecules. So in this little picture or this diagram involving CH3OH, it's only the hydrogen directly bonded to the oxygen that would behave as the hydrogen donor. So again, this is a very common type of question on the AP Chemistry exam, and students often get this wrong. So be very careful when you're drawing lines to indicate hydrogen bonding attractions between two molecules. When comparing the properties of two different liquids, remember that each of the following is a statement that does not compare the relative strength of the intermolecular attractive forces. And we see this all the time at the AP reading, where students will simply list the types of intermolecular attractive forces, but they never compare the relative strength. Students will simply list the boiling points of each substance, or they will state that one substance is a liquid, whereas the other substance is a gas at a certain temperature, but all of those are simply statements and not comparisons. So your explanation of the properties of two liquids, which has to do with, for example, boiling points or vapor pressures, should compare the strength of the intermolecular attractive forces and not just simply list the intermolecular forces or the boiling points or the phases of matter. So always compare the strength of the intermolecular attractive forces. Now, with respect to ion-dipole interactions, review ion-dipole interactions with respect to the following details that are related to the attractions between ions and polar water molecules. Be able to draw the proper orientation of the polar water molecules around the positive ion, the cation, or around the negative ion, the anion. And you can see in these two drawings, I'm showing that the partial negative charge on the oxygen atom of water is pointing toward the positive sodium ion. And then I flip those molecules around so that now the partial positive charge on the hydrogen atoms in water are oriented toward the negative chloride ion. And with respect to the Coulomb's law comparisons, the greater the charge magnitude of the ion, the stronger the attractive force is between the ion and the water molecule. That's the numerator of Coulomb's law. And then the r squared, or the denominator of Coulomb's law, the smaller the ionic radius, the smaller the distance between the ion and the water molecule, and the stronger the attractive force is between the ion and the water molecule. Memorize the information for the 4 types of solids. That would be topic 3.2. be able to identify the type of solid from the experimental data and observations for the solid. Metallic, the solid can conduct electricity. No other type of solid should normally conduct electricity except for metallic solids. Ionic, if the solid does not conduct electricity, but it can conduct electricity when it is melted or dissolved in water, that's a good indication it's going to be an ionic solid. For molecular versus covalent network, neither of these conduct electricity, but the attractions or the intermolecular attractions in a molecular solid are relatively weak, so these solids tend to have low melting points. With covalent network, it's not individual molecules, but an extended network of strong covalent bonds, so these solids tend to have high melting points. And again, last thing here, I had mentioned about vapor pressure and boiling point in this lesson. There's an inverse relationship between the equilibrium vapor pressure of a liquid and the boiling point of a liquid. If you have weaker intermolecular attractive forces, that would correspond to a lower boiling point and a higher vapor pressure. On the other hand, if you have stronger intermolecular attractive forces, that would correspond to a higher boiling point and a lower vapor pressure. And then this last piece of advice, some students think that it's only whenever a liquid boils that vapor pressure becomes a thing. But in fact, a pure sample of a liquid in a sealed container will definitely have a measurable value for its equilibrium vapor pressure, even when the temperature of the liquid is below its normal boiling point. So water can actually have a vapor pressure. Just because it's only at 20 degrees Celsius does not mean it has zero vapor pressure. It's always going to give off a few molecules of that liquid above the surface. So that is my last piece of advice, which means that now we have come to the end of this lesson. In my next lesson, I will give you the chance to review and practice topics 3.4 to 3.6. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which includes the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.